Okay, so to understand how to analyze things going in a circle, we first need to be able to describe the motion, okay? If you can't even describe the motion, like it's a big part of physics, you realize, right? Because in the beginning of the course, we talked about how to describe directions, and then we talk about how to describe positions. And both of them, I use the analogy of if you're talking to your friend over the phone, you should be able to describe unambiguously what situation you're analyzing without needing to FaceTime them, without needing to show them a picture of your finger pointing, oh, there or that way, right? You want a very specific way. So this is a general way of learning in science. Try to make your definitions, make your language precise, so you can communicate the idea precisely. That's the first step in order to be able to analyze something, and that's the only way you can go about and measure something, and then test your theories, test your hypothesis. For example, I have a theory of how fast things rolls down the slope, and now I derive a formula. I can actually go and test them because my wordings are precise. Okay, how about circles? So when things are going in circles, what are relevant things? Let's start with time. Okay, there are a couple. There's two important words. We might be curious about how fast the things will go in a circle. So there's two words sometimes students tend to mess them up and confuse them. One is period and one is frequency. Okay. Now, the easy way to remember this is period. Well, I'll tell you the easy way to remember it, but I'll give you the definition first. First of all, the symbol. Period, we use T, and frequency, we use F. Okay. And you'll see in a second why we're doing this is the definition for a period is the amount of time it takes for one complete cycle. Okay, it's the amount of time it takes for one complete cycle. Okay, and frequency is the number of cycles you will go in 1 second. Okay, it's the number of complete cycles in 1 second. So can I write that in an equation? Remember in physics when someone asks you for definition, there's two ways you can answer that in a test. You can answer either in words or in equation. In equation, you can write this down, right? You can write T, which stands for period, is the amount of time it takes, right? So that means time taken, so delta T, over the number of complete cycles, the number of cycles. I'll just put a subscript for now. Okay, so let's see. So if the number of cycles is 1, then that's the amount of time it takes, right? That's the period, right? So if you go 2 cycles and you measure how much time you traverse 2 cycles, then you just take that time, divide by 2, then that's the time where it takes for 1 cycle. So this looks like a good definition, right? So that's in symbols. Remember, if you write down if you ask the definition, you write it in symbols, make sure you tell people what the symbols are. So for completeness, right, if this is an exam, I'll write below. I don't want to write below because I want to write F below it, so you can compare it in a second. But right directly below here, you want to write T, I mean the period, that's what you're asking for. Delta T is the time taken. And N, or N cycles, is the number of cycles. Okay, very simple, just add a couple of words. You don't need full sentence, you don't need full grammar, just a couple of words to tell people what you mean, because you can use N cycles, someone else can use little n, someone else can use S, I don't know why, but they can use completely different symbols and it could still be correct as long as you tell me what it is, okay? So on the other hand, the flip side is also true. On the contrary, it's also true is if you don't tell me what it is, then I don't know if you meant it correctly or not, because I could have put M over here and I could mean the correct thing, or even if I put N, it does not mean you know what you're doing. So make sure you need to write down what your symbols mean, okay? All right, and then frequency, you can translate this sentence into an equation, and that is the number of cycles per time taken, right? Because it's a number of complete cycles, right? So you will write N is the number of cycles if you want to be complete, add the word complete, right? no pun intended there. So number of complete cycles, right, in 1 second per. So if time taken for not the for 3 cycles, so the frequency is going to be 3, something like that. Okay. So a couple of things. First of all, units. What's the units for number? Well, how many number of cycles? 3 cycles, 4 cycles, it's just a number. There's no meters, there's no seconds, right? Number is a number, okay? So there's no units for number. There's a unit for time, it's in seconds, right? So this is measured in seconds, period is measured in seconds, and frequency is measured in 1/seconds, or seconds to the -1. Now we get lazy, right? Physicists are lazy, so we don't want to write 1/second or second to the -1. So we have a special unit for it. It's called hertz. Now that I think about it, there's more writing to write hertz, but either way. So it's the same thing as 1/seconds. Hertz is just a lazy way to write 1/seconds. Just like newtons is an easy way to write 1 kilogram meter per second square. How do I know that? Well, we have a formula, right? F equals to ma. It's just one example of a formula, but if this formula tells me the unit of F, the unit of F is not going to change from formula to formula, right? If it's one formula is the same, the other is also the same. So what's the standard base SI units for mass? Kilograms, the standard base SI units for acceleration, meter per second square. So what's the base unit for this? We call it Newton, but really it's just a kilogram times meters per second squared. Like that, right? So just like the same thing, hertz is literally identical to 1/seconds. Okay, so if you're in an exam, if you write how 3 hertz, 5 hertz, or 3 per second, 5 per second, both would be completely fine. It's no difference at all. Okay, so if someone says the motion is going in 5 hertz, what they mean is it's going through 5 cycles per second. That's pretty fast, but yeah, depends on how big your circle is, I guess. Yeah, okay, so comment number 2, you notice that this is just the reciprocal of this. So there is a simple relationship between these two, and it is, so the period is identical to 1/f, and this is a useful identity to remember. Okay, I'm emphasizing that it's identity. You can write equal if you want. It is equal, but just like sometimes we want to emphasize something, right? Like this means it's identical to. I don't care what number of cycles, how much time it takes. The period is always 1/f. I want to emphasize that. Okay, and the last comment is back to my first thing to say is how do you remember which is which? Sometimes students find it very confusing to between them. Well, the hint is over here. The symbol is T. So period is about time. So it's always time taken for 1 complete cycle. And frequency is, swap it around, it's number. So frequency is related to number. Period is related to time. Okay, so that's the trick I use to remember it. You can use whatever trick you like, but that's the trick I use to remember which one's which way. Okay, good. So we talked about 2 jargons, period and frequency. Another one is okay, so we talk about time, but how about can we measure the position? Okay, remember position is a big deal about talking about positions in kinematics. Well, you can talk about the origin and stuff like that. Should I put here as the origin or should I put here as the origin? What's a good choice? Well, obviously the physics should not depend on where you put the origin, but there's a better way to describe where the object is with respect to the circular motion. Okay, you can tell me the radius of it, okay, the circle that the object is. Now assume the object is already going in circular motion. You just need to tell me the radius, and you can tell me the angle. And which angle? It's conventional to just use the polar angle. Okay, but you are free to define where you go, where you start your angle. But a common place to start is using the polar angle to start, and that means starting from the right hand side. Again, it really doesn't matter. Okay, so in fact, to illustrate that it doesn't matter, let me arbitrarily say, hey, I want to call this part theta equals 0, right? Normally we call this theta equals 0, like that. But let's say I want to call this theta equals 0. And my object is over here. So the starting point, theta, is theta naught. And after some time t, right, theta as a function of t, let's say theta at time equals to 0 is theta naught. Okay, so this angle here is theta naught. And because this is my origin angle, and over here, that's just theta final, something like that. Okay, and so this is theta final, like this. Okay, so you can describe things in terms of angles. And now if the object goes from here to here, instead of talking, because it's going in a circle, it doesn't make a lot of sense to talk about the displacement. The displacement will be this, right? Would be this vector going from here to here, the final position minus initial position. But it's better to talk about the angular displacement, delta theta. So that's the change. Remember, delta means change, right? So that's the change in theta. You go from here to here, okay? So let me write that down. So this, we talk about angular displacement a lot, okay? The symbol for it, delta theta. And the definition is just the final angle minus the initial angle. But remember, whenever you talk about angles, you always need to set an origin. But this time you set an origin angle. Okay. And this is, at first it sounds weird, but you can always contrast that with what now I will now emphasize as linear displacement. And remember what's linear displacement? In Suvat variable, I call it S, but what really it is delta x, right? So the linear displacement is x final minus xi, but x makes no sense until it's completely meaningless, until you set the origin. Excuse me. So until you set the original position. So you need to set somewhere as x equals to 0. Then xi and xf make sense. Then delta x would make sense. The same thing, you need to set somewhere as theta equals to 0. Then you do that. But a lot of times, maybe not a lot, maybe let's say just over 50% of the time, things will start over here, and it will just be natural to set that as 0, because if you set this as 0 instead of this, then this angle, whatever the polar angle is the angular displacement. Okay, right? Because if you set that as 0, then whatever the polar angle is, that is exactly the same as the displacement. All right. And finally, so once you understand this, it brings us to, last but not least, the concept of angular velocity. Again, it's used if a lot of students finds that confusing, but again, the easiest way to understand that is contrast that with linear velocity. Okay, it's just the velocity we've been talking about all along, but now I'm emphasizing it's linear. So what was the definition of, well, the symbol was V for it. And what was the definition? Let's start with the average. Average linear, both of them can be average or instantaneous. The average linear velocity is delta x over delta t, right? The instantaneous velocity is dx dt. If you want to write that in words, it's the rate of change of displacement. Okay. Rate of change just means this is identical to, so it just means ddt. Anything with ddt translates to rate of change of displacement, like that. So that's the keywords there. Angular velocity is given by the symbol omega. Okay, and yes, this is omega, not w. Okay, it's a little bit curly. You can Google how a typesetting omega looks, right? It's a lowercase omega. Capital case omega is this. It's the Greek letter for omega. Capital K, uppercase, lowercase, like that. My professor used to joke the difference between a 2-year community college and a 4-year college is how you pronounce this symbol. So if you pronounce it omega, we know where you studied. But joke aside, I don't really mind what you call it, but might as well tell you the proper name. You know, just like you feel free to call this a triangle, but I'm going to call it delta. That's its proper name. Don't ask me why they use omega. I have no idea. But yeah, let's stick with that, right? So the average angular velocity doesn't even look angular, but it looks like a circle. Let's go with that. Is defined as the change, not in change in displacement, not the linear displacement, but the change in angular displacement. Basically, how much angle you have moved in a given time taken. Okay, so this tells you how much meters, how many meters you've moved in certain amount of seconds. This tells you how much angle you moved. Okay, so maybe like 30 degrees per second. So it means every second you rotate, because we're now talking about circular motion, right? So it's much more convenient to talk about angular velocity than this. We will actually talk about this as well, but yeah, so you understand there's a new concept. This tells you how many meters per second. That tells you the units as well, meters per second. This tells you angle per second, okay? What units should we use for angles? Most of the time, we're gonna go with radians, not degrees, okay? And we'll talk about that in the next video as well. But yeah, so but both technically works, but radians is much more convenient angles. Otherwise, you'll have a lot of 360 degrees floating around. If you do radians, there's no random numbers floating around. Okay, so angular velocity, this is average angular velocity, but same thing, you can define instantaneous angular velocity, which is the rate of change of angle. Same thing as this. So more properly, right, it's the rate of change of angular displacement. You can kind of be sloppy and say rate of change of angle, but yeah, but rigorously, you can call that, if you want, you emphasize this linear displacement as well. Okay, all right. Oh yeah, you can also do angular acceleration. We won't talk about it too much, at least in the first part. Yeah, but just for completeness, maybe I'll add it here, right? Angular acceleration. The symbol is alpha. Again, we use the Greek letters for everything angle, right? We used x, v, and a. So if we use theta for angle, might as well just change them to all Greek. So that's theta, omega, and you can have average angular acceleration, right? So that's the change in angular velocity over the time taken, but the instantaneous angular acceleration is the instantaneous rate of change of this. Okay, we won't talk about it too much. So it's the same thing as the linear. It's a direct generalization, right? dv dt instead you do d omega dt. Okay. And the reason we are not going to talk about this too much is because we are going to talk about special cases where it's the angular velocity is constant. So it's going to go at a constant speed around, right? So what's the constant angular speed? Same thing, angular speed is the magnitude of that. So the angular speed is going to be constant, which means does it accelerate? Will the angle accelerate? No. So we're going to talk about a special case where this is zero. At every instant, this is the instantaneous one. At every instant, the angular acceleration is zero. So the angle doesn't accelerate, right? It goes at a constant angle per unit time. That way, so it doesn't accelerate, which means the average is just at every instant is zero. That means the average is zero, right? At every instant over here is zero, so the average is still zero. And we're going to focus on a case where this is constant, okay? Angular velocity is constant. And this is what uniform circular motion is. Another way to say is you can say it's uniform speed or uniform angular speed. It's the same thing, okay?